Welcome to our presentation on continuous time state and dynamics estimation using a pseudo-spectral parameterization. State estimation is the problem of estimating pose and velocity of a body using only sensor measurements. Current approaches use Kalman filtering or factor graphs in an effort to tackle this problem using an underlying continuous time parameterization. These are commonly used as Gaussian processes, B-splines, or Beaver decompositions. Dynamics estimation is the problem of estimating the dynamical parameters of the body, such as the geometric and inertial parameters, the external forces such as gravity, and detecting collisions and other wrench forces. In this paper, we propose to do both state and dynamics estimation simultaneously, with the idea being that the state estimates constrain the dynamics and vice versa. We use a common polynomial basis for the joint optimization using only camera image measurements. We leverage Chebyshev polynomials as the orthogonal basis, which we will describe in the next slide. Chebyshev polynomials are basically cosine functions of varying degrees, which when projected from a circle to a line, give us a orthogonal basis. From the first row, you can see the cosine functions plotted on the circle when projected form the second row, which is the set of polynomials. Chebyshev polynomials have very attractive properties, such as providing us with easy differentiation and being easy to evaluate using the barocentric interpolation formula. Chebyshev points are special collocation points, which are equidistant points on a semicircle, which when projected to the x-axis, give us points which cluster around the ends. These have superior numerical properties as well as avoid the Runge effect. We use pseudo-spectral parameterization, which involves estimating the underlying function using the function values at specifically chosen points, which are, in our case, the collocation points. We use the Chebyshev points as our collocation points due to their superior properties. Our estimation is done in a factor graph-based framework. We estimate two values, the state matrix X and the control matrix U. D is the degree of the polynomial. For example, it is 12 for a quadrilateral, 3 for translation, 3 for rotation, 3 for linear velocity, and 3 for angular velocity. The black factors are measurement factors, in our case, camera image measurements, and the red factors are dynamics defects factors. These factors constrain the control to be plausible given the current state, and there are as many dynamics defects factors as there are number of Chebyshev points in the underlying polynomial. For our experiments, we use the FlightGoggles Simulator. It is a rich UAV simulation environment with photorealistic rendering via Unity. It also supports raw-based collection of data and experimentation. We ran 4 different trajectories of the simulation, each of which are non-trivial and involves some particular maneuver. We use these as our evaluation basis. Here we display the state estimation results showing the ground truth trajectory and the estimated trajectory. These are qualitative results, and as can be seen, the estimates are very accurate. As per on the absolute trajectory error, it is less than 1% relative error. And 1%. More importantly, we can also perform control estimates of the quad-rotor motors. In this case, as you can see, the dashed line is the true motor speeds, and the dotted line is our estimate. As can be seen, the dotted line follows the dashed line in terms of trends. This is applicable not only for the first scenario, but for the other 2 scenarios as well. In summary, we perform joint state and dynamics estimation using a Chebyshev polynomial basis. Our estimation is based on a factor graph-based optimization process, and we perform and demonstrate results in simulation with a relative control error of less than 1%. Thank you.